Hi Year 10, sorry we're not able to be having this lesson in person. So we are going to be starting a new topic now, looking at structure and bonding, and we're going to be kicking this off with states of matter and chemical bonding. And by the end of this, we should be able to describe the changes of state and the properties of each state of matter.
So 5 starter questions for you. Pause the video, have a go at them, and then on the next slide I will go through the answers. So our group number of our periodic table tells you the number of electrons that you have in the outer shell. So for example, oxygen is in group 6, and this means that it has 6 electrons in the outer shell. The 3 subatomic particles, their relative masses and charges. So our proton has a relative mass of 1 and a charge of +1. Make sure it's a +1. If you haven't put a plus or a minus, you must ensure that you do a plus or a minus, because this is telling us whether it's positively charged or negatively charged. Electrons, they have a relative mass of 1/200 or negligeable, so it's not really considered significant compared to the mass of protons and neutrons. And electrons have a charge of -1. Our neutron has a relative mass of 1 and a charge of 0, so it's neutral. Draw the structure of lithium and the ion that it forms.
So lithium in the periodic table has an atomic number of 3 and a relative atomic mass of 7. So our 3 tells us that there are 3 protons, and our 7 tells us that there must be 7 protons and neutrons. So 3 protons plus 4 neutrons to make that 7. For an atom, we're also going to have 3 electrons. So for our atom of lithium, we're going to have 1, 2, 3, 4 neutrons plus 1, 2, 3 protons in our nucleus, and then our inner shell is going to have 2 electrons and our outer shell 1 electron, as it's in group 1. For our lithium ion, it's going to be losing this 1 electron in the outer shell, as it's more stable having a full shell, and so it's easiest to just lose 1 electron rather than gain 7 electrons for that stability. So for our lithium ion, we're still having the same number of neutrons and same number of protons. Really crucial that we have the same number of protons, as this is what defines the type of element. So 1, 2, 3 protons, still same number of neutrons, and then instead of 3 electrons we now just have 2. And in order to show the charge, so it's lost 1 negative charge, so this now becomes positively charged. So we draw square brackets around it with a plus outside to show that that entire thing has a charge of +1.
Draw the structure of fluorine and the ion it forms.
For fluorine, in the periodic table, it has an atomic number of 9 and a relative atomic mass of 18. So we know there are 9 protons, and therefore for our mass it's going to be 9 protons plus 9 neutrons. So for our atom of fluorine, 1, 2, 3, 4, 5, 6, 7, 8, 9 neutrons, and then 1, 2, 3, 4, 5, 6, 7, 8, 9 protons. For an atom, we're going to have 9 electrons. So inner shell can only have 2. Our other shells can go up to 8. But in this case, we only need 7 in our second shell in order to make 9, so it's got 1 unpaired. For our ion, of fluorine, which we call fluoride, so F minus. It's -1 charge, as it just needs to gain 1 electron in order to make that outer shell full for that stability. So our nucleus would look exactly the same. I'm just going to draw it like that to save your time. And then we would have our original 7 electrons plus 1 electron that it's gained from somewhere else, and again drawing these square brackets with a negative charge to show that that entire thing is charged. This is our nucleus, which is this in that diagram, so that they would be exactly the same, as we're not changing the nucleus when we make ions.
And then finding the difference between a compound and a mixture. So a compound, for example, carbon dioxide, this is made of more than one type of atom chemically bonded together. So in carbon dioxide we have 1 carbon atom which is chemically bonded to 2 oxygen atoms. And then a mixture such as salt water, that contains more than one substance, so in this case salt and water, but the substances are not bonded together, and so we can separate these easily. So salt water, if we want the salt, we can evaporate off the water, whereas if we want the water, we can distill that off. So just a recap of particle theory. So in particle theory, we assume that the particles in our diagrams are all the same substances. So what I'd like you to do now is to click on the hyperlink. It's included in the instructions and also in the PowerPoint, and this will take you onto a website to look at simulations. So when you click the link, you should come up to a page like this, and if you click on the states, you then have a diagram that looks like this. On the right hand side you have solid, liquid or gas, and so I would like you to go between the three, looking at the way in which the particles are moving, how they're arranged, have a play with what happens when you change the temperature, when you raise it, lower it, etc. You might also want to have a play using different atoms or molecules or compounds and see what happens with those. I also want you to consider what the limitations of this model is, and I'm going to ask you to pause now while you have a go with this. With this model, you can see with our neon, our particles nicely in a straight line, whereas water, they look a bit different even though we're still a solid. And one of the limitations of these particles is it's not including any forces of interaction that are happening between these molecules. So in our water, there are actually some forces of interaction between these molecules, and that's what's making them more spaced out compared to that neon structure where they're much more in a regular arrangement compared to the water. Argon, you can see it in nice lines, and similarly with oxygen. So water, something about these intermolecular forces that this model doesn't actually show us is a limitation of this model. So those forces that I was talking about, these are what are needed to overcome in order for us to melt and in order for us to boil. So the stronger those forces are, the higher our melting and boiling points. Take a look at each of these phases in turn. So to start with our solid, so we can think about our solid in 3 different perspectives. So we can look at what we visually see, so the macroscopic, how we visually see solids. So if we stick with this idea of water, how we see water as a solid is we see it as ice. So cubes of ice, even small crushed ice, we're still viewing it as that solid. But actually what we need to do when we're considering the particles of water is we need to look submicroscopic, so below that level, so that we can see the particles. Now this particle diagram compared to the simulation, we've seen in that simulation there are clearly some forces between the water molecules, so they don't actually have this regular arrangement for our water molecules. However, this is our typical diagram for a solid, so we would say that they have a regular arrangement, and as we saw in the simulation, they do move, they vibrate, but they stay around that fixed point, so they're not moving off in different directions, so we say they vibrate around a fixed point. So key points, regular arrangement, vibrating around a fixed point. And then the symbols. So state symbols you will hopefully have come across before, but that S in brackets shows us that that water is in a solid state. So going now to liquid. When we think of liquid water, well, we think of water from the tap, water in a glass, water in the sea. So that's our macroscopic view of liquid water, what we can see. But again, going below to that particle level, again, looks different to the simulation that you used because we're not showing all the atoms of the water molecule nor the forces between them. But here we can see that they fill the bottom of that container more. If you put an ice cube into a glass, it wouldn't fill the bottom of the glass like it does if you poured the same volume of water in. So with liquids, they fill the base of the container. And as you will have seen in the simulation, those particles in the liquid state, they're able to move around a lot more along that base. They have that more freedom to move around. Again, looking at our symbolic, this time instead of an S, we've got an L in brackets. And this is because it's a liquid, L for liquid. Notice that these state symbols, both in the solid and the liquid, they're lowercase letters. So we always use lowercase letters for our state symbols, and that's because we use capital letters for our elements. For gas, in terms of water, in terms of what we see, we often think of steam, so coming off a kettle. If you've been to like dry cleaners where they're steaming clothes, that's what we see when we see water in a gaseous state. For our particle level, what you can see in this diagram, again, doesn't quite look like the water particles we saw in the simulation. It's a much more simplistic view. However, what should be clear is that it's filling the space it can. So it doesn't stay at the base of the container. It will fill the container, and in this case, the container doesn't have a roof, so it could escape from that container. And when I say roof, I mean lid. These particles, they're moving much quickly. They're moving around more randomly in more directions. They have a lot more freedom in order to be moving. Turning now to the symbol, now we use a G for gas as our state symbol. So if you pause the video now and fill in your particle diagram worksheet, drawing a diagram for each of the states and also a description of those particles in those states. Okay, so with our phase changes, I've asked you to copy down this diagram. So if you just pause the video and copy down the diagram, one minor modification though is vaporization. That's more an American term, which is where this image has come from. So if you swap that out for evaporation, which is the term that you will be more familiar with. So going from solid to liquid to gas, we've talked about the arrangement of our particles and the movement of particles. If something's moving a lot, so thinking back to our energy topic, where you talked about kinetic energy being the energy relating to movement. So going from solid to liquid to gas, our particles are moving around more, and that's because they have more kinetic energy. So going from left to right in this diagram, the particles are gaining more energy, so they have more energy to be moving around. Going from right to left, so gas to liquid to solid, they don't have as much energy, and so they're not moving around as much. So thinking about our melting points and our boiling points, these are successively higher in temperature, and that's because at higher temperatures you're supplying those particles with more energy, and so therefore they're able to move around more. Phase changes. So these are the changes between our different states. So going from solid to liquid to gas, or we could actually go straight from solid to gas, or from gas to solid. One of the instances of solid to gas you may be familiar with is in movies when they use the smoke effects, they're using dry ice, so solid, that then sublimes straight to gas to create that smoke effect. The ones you will hopefully be familiar with though is going from solid to liquid, which is melting, liquid to gas. Here they've put vaporization, but often we would call it evaporation. So when you're doing this diagram, I would use evaporation. Going from gas to liquid is condensation, so just like you get on the windows when your room's warm but it's cold outside, you get some condensation going on. So that's the water vapour going into liquid, water vapour coming from the atmosphere. And then liquid to solid, so that's freezing. We put water into the freezer, it turns into ice. Deposition is the reverse of sublimation, so going straight from a gas to a solid. Now, you are quite familiar with ice melting, evaporating water, freezing water, so I think you already have an idea that these changes are reversible. Now, these changes are called physical changes because they're not forming new substances. In each of these cases, it's still water. And you'll notice on the previous slides, the symbols that we used was always H2O because it's the same molecule, the same atoms bonded together. They haven't changed. However, what has changed is the way in which they're moving, chemical changes. So this happens when our atoms change the way in which they are bonded. So as in reactions, we have chemical changes where our bonds are broken and where bonds are made. Some of these chemical changes are reversible, however many are irreversible, and an easy example for this is making toast. When you put bread in the toaster and turn on the toaster, you end up getting toast, but you couldn't then go back to having bread. So there are 3 types of chemical bonding that we're going to look at over the next series of lessons. So ionic bonding, this happens between our metals and our non-metals as a result of them forming ions. Now ions is something that we looked at in last year's previous topic of atoms, so hopefully we can remind ourselves of those. Metallic bonding occurs in metals, and then covalent bonding occurs in non-metals. And like I said, we'll look at each of these in more detail over the series of lessons. With our atoms, if we take a single atom, they alone do not have the bulk physical properties because our physical properties depend on the type of bonding, so the 3 that we talked about, and also the structure of the substance. So you can't just take an atom of oxygen and say it's going to have a low melting point. It's as a result of the bonding and the structure in which it forms. When we get a solid, that's a result of the temperature at which it's at is less than its melting point. With a gas, the temperature it's at is above the boiling point, and a liquid, it's where the temperature we are at is in between the melting and boiling points, so greater than the melting point but less than the boiling point. So you now have questions to answer, so pause the video and then come back to it when you've answered those questions. So 2 questions now based on the previous table. So you need to be able to predict the state of oxygen and bromine at the temperatures given, and you've been given the melting and boiling points for each of these. So if you pause the video now, and then we will go through the answers. So in both of these cases, they are liquid, and that's because in both of these cases, our temperature that we've been given is in between our melting point and our boiling point. So minus 200 is higher than minus 218, but it's less than minus 183. This one was actually probably the harder of the two questions because it's a bit counterintuitive when we're thinking about our negative scale. So when we're thinking about temperatures being greater than, we're thinking about moving towards the positive end of a number line. With our bromine, 25 degrees is our room temperature, roughly. And so 25 degrees Celsius is above 7 degrees and less than 59 degrees. So again, liquid at that temperature. Describe the states, the changes of state and the properties of each state of matter. On the next two slides are the information that you need. So the description of the states and the description of the changes of states. So what I would like you to do when you're answering this question is really think about how you're structuring your writing and what key terminology you can be using. So not just saying going from solid to liquid to gas. Talk about those phase changes using the diagram that you copied down, talking about it in terms of the energy of the particles. You should then submit your answer to this in our class in Microsoft Teams. If you have any problems with this, do send me an email.